Yes, so welcome back. We really enjoyed a bit extended time of the tea break. I hope you benefited from it. The time was a bit extended due to one paper in the morning that didn't link with us online. Now we are at a time to start the following session, which is the fifth session. This session will have 4 papers. It will be moderated by Mr. Kral Ivan and Dr. Wolfram Scholes. Sorry if I mispronounce. They will introduce the presenters and the paper details. Allow me to say a few words about our great moderators. Mr. Kral Ivan, he is from UNIDO. He is project manager at UNIDO Agribusiness Development Department with responsibility for the development, funding, and the implementation of technical cooperation projects in laser industry sector. He is also chairman of the International Training Commission of the IULTCS. He authored and co-authored several guidelines and papers for laser value chain, just to mention few of them, as he is a very seasoned experiencer with a number of years of experience. I could not list out all his qualifications and all his previous activities. The second moderator, which we are honored to have him together with us in this hall, who traveled all the distance to join us here in Addis, is Dr. Wolfram. Dr. Wolfram Scholes from Austria is the chairman of the Environmental Commission of the IULTCS, IUE of the IULTCS. He coordinates the dissemination of new environmental development in each country, research and development activities, legislations, and ecological developments. He is fellow member of the SLTC, the UK Society of Laser Technologists and Chemists. Dr. Wolfram is also company director of the engineering company of W2O environments currently. I think in brief, these are some of the introductory few words about our great moderators. Now allow me to pass the floor to our moderators. Over to you. Thank you very much.
Thank you and good morning. I'm sorry that I'm not able to be present in Addis, but due to travel restrictions, I am able to participate also only online, but I really appreciate all these previous presentations. This session will be started with a very important topic, and it is a carbon footprint in Italy, communication tool supporting environment and climate efforts. It will be presented by Mr. Daniele Pernigotti. Mr. Pernigotti, he has over 15 years of experience in the field of environmental certification. He is also CEO of Equilibria and environmental consultancy in leather and carbon management in leather sector. He is representing also Italy in technical Commission for ISO 14067 for carbon footprint, chair of Senate Technical Committee 467 on climate change, and also a lead assessor of greenhouse gases emissions and technical expert for Accreditia Italy, ANSI in the USA, ONAS in Colombia, also in Dutch, and IA per evaluator. So, Mr. Pernigotti, please go ahead with your presentation.
Thank you, everybody, to allow me to give this presentation today. Please confirm me if you are able to see the screen as in the correct mode. Okay, thank you so much. Yes, also thank you for the introduction, because as you've seen, the strong experience in the standardization area. I skipped this slide. And but I also the director of a specific program operator on carbon footprint, this Carbon Footprint Italy, and this is the opportunity for me to give you some feedback, some experience, to share experience on this specific point. I'm now at the COP26 in Glasgow, and we have several presentations on carbon footprinting because it's growing topics, very at the center of the interest. Also for the negotiation area. So let me start with some introduction. The ISO standard on climate change or carbon management in particular are mainly focused on two specific areas, the product and organization. Obviously, the methodology for the quantification of greenhouse gases are similar, but it's the different approach that we may use for product organization that require different context. For this reason, I like to give some more explanation on product. Carbon footprint of product is the ISO 14067 is a tool to evaluate the contribution on climate change of a specific product, taking into consideration the sum of greenhouse gases emitted and removed along the full life cycle of the product. So we consider only one impact category, that is climate change, but behind there is a methodology, it is life cycle assessment, that is very stable, very known. This methodology has been developed in the 1970, was mainly developed for research purpose at the beginning to understand more in depth the impact of each product. And this implies that when we approach for the carbon footprint of product, according to ISO 14067, we need to consider the full life cycle from cradle to grave, generically. But in some specific case, like for the leather product, we may go in direction of cradle to gate to stop the assessment, the quantification of greenhouse gases to the gate of the tannery company. This is important because not always we know the final use of the product, so we don't know the function, the final functional unit. The other area is the organization, and here we have another standard, ISO 14064 Part 1, and the idea is to consider the impact of a company in the global meaning. So you see here that with the new revision of the standard, there are similar approaches that we already saw for the carbon footprint of product. Because you see, there is a raw material, supplier, manufacturing, distribution, customer, consumer. So in some way, there's extension of the attention from the real core business of the company to the full value chain. Maybe most of you know the scope 1, scope 2, and scope 3 approach is the way to consider the extension of responsibility of the company from the direct emission to the indirect emission in connection with the electricity consumption to the full indirect emission. So this is a kind of expansion from scope 1 to scope 3. Okay, but now we have a quantification. We have very reliable data because we follow ISO standards, and then we go in the domain of communication. And here the confusion starts because there is a lot of label mark. Every day you see new label available on the market, and some of these labels are safety declaration. And there is a high risk to be confused with the greenwashing because it's difficult to understand behind the label what is the value, the real value of the quantification that support the label. For this reason, in several countries has been developed a program operator for the communication of footprint. This is our experience as carbon footprint Italy to in some way give more clarity in the market where there are self-declaration, to ensure a proper communication between the client and supplier, and also to keep in mind that there are a lot of ISO standards available on the market, and then we want to have a consistent approach that is valuable at the international level. So key features. As mentioned before, all the program is based on ISO standard. 14067 and 14064 part 1 for the quantification of emission in connection product organization. 14064 part 3 and 65 for verification and accreditation of the third-party verifiers, and 40026 on the communication of footprint information. So you see that all the package is consistent, and this is very important. I will give some more information at the end of the presentation on this specific point. So when a company or product decides to be part of our program, they receive a label, and the label is combined with the QR code. And the QR code is important because is the direct connection with the background information. The background information is fundamental because it's supporting the label. The label is recognizable, but then you need to have the background information. And this is an example of a leather company, leather product in this case. You see the certificates on the bottom left part, then you see the recognition of the company, the product, the reference person, contact person, and the specific technical detail. All this information verified by third party. So very reliable information that is supported a very easy recognizable label from the other side. And this also happened for the organization side. Another important aspect of our program that is very innovative at the international level, we are the first program using blockchain technology. That is very important in this case because through the blockchain technology, we have unmodifiable information on the network. So in some way, when the company decided to have a commitment for reduction of greenhouse gases, we give the fixed baseline, the starting point. It's not modifiable. So it's very transparent to show year by year how is the modification from the initial emission. And this is fundamental. Some result and discussion. So all of you probably recognize that there is a growing interest or request of information from the client and customers on carbon footprints. We receive, I don't want to say every day, but say every month at least, some information from a client that want to have more clarity on the emission, greenhouse gas emission of a product. So, and this is also an interesting opportunity in the direction of the value chains, because this kind of tool is powerful when there is cooperation, coordination in the value chain. So to have a supplier working together with a client is very important also to maintain the business in the future. And then in this particular moment, when this activity is in the starting phase, there's also a possibility to differentiate the own company in respect to the competitors, and then to take a better position on the market. And this is an example of value chain. This is only to show you the idea behind. We have a company producing chemical products for leather sector. We have a leather product, and we have the client that is, in this case, the footwear, outdoor footwear producer. You may understand the add value, because the producer of footwear want to have a reliable information on the leather, that want to have reliable information on the chemical products. So you may imagine this kind of network growing always more. There was the day before yesterday, I was at the UN pavilion when in the Innovation Hub, there was a presentation by World Business Council on Sustainable Development on the need to have reliable information on the value chain network. Because the big company want to have always easy, prompt information from their supplier. And then this channel is fundamental to guarantee the collaboration in the business for the future. And we are working always more in this specific area. We developed the first PCR, I think more than 50 years ago. The PCR is a product category rules that is necessary for the development of LCA and the carbon footprint of product. The first PCR of the leather product almost 50 years ago. And but now we are working more in direction to better understand the impact of the upstream phases, as well as in the downstream with the producer of leather products. And now we go to the specific situation of the leather sector. You have the experience, the day-by-day experience on how luxury fashion and automotive companies are moving in the direction of carbon neutrality. There are a lot of claim commitment in the direction of carbon neutrality. And this implies always more what I anticipated before, the request of information and transparency on their value chain and their supplier. And you know that the chain of custody, for example, is an example of the request of collaboration in the value chain, but the carbon footprint information is really key. And the experience, the Italian experience is not the only one. We have several countries that develop the carbon footprint program operators. We have some example here. And a network has been created. And the network is the opportunity to work all together in the same direction. And the first two program operators that signed a memorandum of understanding for a deeper collaboration was Carbon Footprint Italy, and the Climate Registry is a Californian program working in the West US and West Canada. And this happened in February. Tomorrow, we will have another signature, will be the inclusion of a New Zealand program operator. And there was the Minister for Costa Rica. They will sign also for the Costa Rica program for carbon neutrality. So you see, it's a growing movement because the idea is to have at the end a one recognized label that is recognized in all the different countries. And I go to the conclusion. The first point, you see there are a growing number of standards for sectoral standard, local standard that are pretending to be recognized on the market. But the reality is that the ISO standard is internationally recognized. And this is fundamental if if your intention is to work through different countries. Then the point of the communication is fundamental to have third-party verification and third-party communication to give credibility to the market, because otherwise there is a high risk to lose all the credibility. And then the use of carbon footprint label, in our view, is the most effective way to transfer this kind of information to the growing demands of the customers. So thank you so much for your attention. And obviously, I'm more than happy to give you any possible answers.
So many thanks for very interesting presentation. And I'm sure that there will be a lot of questions after the session, as transparency and carbon footprint in the leather industry is very important topic. Many thanks.
Thank you.
Great. So Tom is Satra's technical advisor, and his experience includes leading the core Satra Innovation and Research Department, which is at the leading edge of applied technology targeted at materials, products, and process improvements and developments within manufacturing industries. And Tom has been involved in various developments and has co-authored 6 research papers on the complex mathematical backgrounds to leather cutting software, 4 of which have been published internationally. He joined Satra in 1984, and Satra is an independent research and testing organization, which was founded in 1919 in the UK and is serving customers mainly in the leather industry around the world. Thank you very much. Tom, go ahead, please, with your very interesting presentation.
Hi, everybody. My name's Tom Bayes. I'm a technical advisor for Satra. I actually was head of innovation for many years, probably about a decade. And I'm going to talk to you today about around the subject, is leather still the material of choice for footwear? Well, I believe so. And one of the reasons I believe so is I think leather's beautiful. For a start off, leather's very durable. It's a very durable material. It flexes well. It behaves nicely. It's good for processes, etc., etc. Leather's also very comfortable. It exhibits a lot of the materials properties that we're looking for in footwear, in terms of breathability, in terms of cosseting, the way it forms the footwear, the foot shape, etc. And it also has other properties as well. I mean, we can make it waterproof, for example, make it highly water resistant. We can make it look nice. We can give it different colours, etc., etc. Leather, and obviously we're going to talk about sustainability. Is the main theme, I suppose. Leather's very repairable. We can repair it. It doesn't fray. It stands being restitched many times. It can be disassembled fairly easily, being cut and closed. Which brings me around to another point, it's restorable. You can use leather care products to restore the look and the aesthetics of the leather, almost back to as new condition. And don't forget, it's already a byproduct. It's already a byproduct of the meat and dairy system, which I'll mention very briefly in a moment. And leather has many properties favourable for footwear as well. It's easily cut. It's easily die cut with knives. I've already mentioned it's easy to stitch. It doesn't fray. And that suits a lot of the shoemaking processes that we employ in the modern shoe factory. It conforms to shape. We're taking a 2-dimensional shape and we're trying to recreate the 3-dimensional shape of the last. And using heat and moisture, this is more than possible to do. And it retains its shape quite well if it's conditioned correctly in that process. Lastly on this slide, many synthetics, of course, still strive to be like leather, as good as leather. All the things that leather offer, from the things I've talked about, abrasion resistance, etc. At this point, you're thinking, I'm a leather guy. I am. I have footwear that looks like that. But remember, my job also involves dealing with some quite exotic and technical textiles and synthetic materials. So there are special cases where some of these synthetics are really very, very good. But today we're talking about leather. We're talking about the properties of leather. Excuse me. I think that we do tend to let leather sell itself. We don't tend to market it particularly well. It does sell itself. It's very good at doing that. And I think we can't just sit back and expect the leather itself to speak for itself. We have to speak for it. We have to keep doing that. And really, I think that's bringing me down to one of the cruxes of the matter, that if you like leather and you're a leather producer, manufacturer, we're kind of at war with a little bit of misinformation that's going on right now. And I want to put ideology and politics in a little box somewhere and put it away, because I'm a scientist. So I don't really want to get into that. But there's an old English saying that if good men do nothing, then evil will preside. And you know, we do need to tell the good story of leather. We need to speak on its behalf, and we need to correct misinterpretations. And we do have some work to do, and we do have some work to do, especially on the sustainability aspect. So I'm just going to talk very briefly, because we haven't got long, about sustainability. The good example is world population. There we go. Obviously, if we go back a long time to 10,000 BC, there was only about 4 million people on the planet, which is not very many. This has been increasing until a bit of a crucial date is actually 1804, which is the first time we reckon that there was actually 1 billion people on the planet, and that has now grown very quickly to 8 billion. And it's an interesting aside fact that about somewhere between 7 to 10% of all humans that have ever lived are alive right now. And do you know what they all want? They all want footwear. They all want shoes. Keep in mind the sort of 1804 to 1927 level of population there. We are currently rampant consumers, and we rampantly consume our resources, our planet's resources. And this is to do, obviously, with changes in lifestyle and wealth, of course. And it has a nickname, like all these things, called affluenza, a disease that we suffer from, apparently. But I want to make a point here that it's not just to do with the population increase. If you look at the people who were born and lived around the 1900s, around the turn of the last century, we don't consume footwear as if we're 8 billion of those. We consume footwear at about the rate of 90 billion of those people. Okay, but roughly about 10 times as much as those people did. Of course, those people had shoes that they bought, they repaired them, and they lasted for years in some cases, where now our shoes don't last very long, do they? So we consume footwear at an enormously high rate. I can compare that with water. We actually looked up some figures for another webinar I did a while ago. We actually consume water at the rate of about 7,500 billion of people that would have been around in 1900s. So it's not just the increase of population that's the problem, it's this logarithmic increase in consumption and the rate we consume resources. The end of disposal is landfill. 85% of footwear ends its life in landfill. In Europe, that's about 1.5 million tons a year. It's a significant amount. In the UK, it's about roughly 150,000 metric tons a year. And that's a very difficult number to obviously picture in your mind. But if you think around 4,000 to 5,000 truckloads, they're 44-ton trucks, a year, in terms of what we bury in the ground. And when we talk about landfill now, it's full, isn't it? We build mountains now. We build mountains of rubbish, and then what we do is we cover them in a metre or so of soil and turf, and forget about them. And on the left there's a picture there of that's actually in the UK. The grass on top of that bank is actually pasture land where cattle are grazing. And you can see there that's been erosion of that bank, and you can see exposed there about probably 10 or 12 centimetre layer of compressed rubbish from an ancient landfill, from a landfill that could be 100 years old. No one knows what's in it. And this is the problem. Okay, this is one of the problems of disposing of things just by burying them. And of course, then this responsibly buried material then becomes into the environment. It's let go, it ends up in rivers and all sorts of things. Now, If you bury something in the ground, that's called anaerobic decomposition. That produces methane, and as we're probably all aware, methane is one of the major one of the major gases that's bad for the climate. So landfill results in CH4, which is methane. Anaerobic decomposition, that just means in the presence of oxygen. And this is like composting, for example, that produces CO2. So this idea about biodegradability, you've got two choices there really. You can bury it in the land and forget about it, and that's methane, and you can decompose it aerobically, and that's carbon dioxide. Now, if you take fossil resources like coal, oil, natural gas, of course, comes from anaerobic composition. That's where you get natural gas sitting above oil seams because of natural gas is methane. And that's an interesting cycle, but it takes about 300 million years for that natural cycle to complete. And as far as we're aware, I think it's only ever happened once. Okay, and this is fossil carbon, new carbon, and that's basically what plastic is made of. Okay, so it's new carbon from a fossil source, a very ancient fossil source. Biological sources, and I've just picked a hide as an example, and you might have noticed that we don't walk around picking our way between endless dead things, is made of atmospheric carbon, and that returns to the atmosphere quite quickly. In fact, it returns naturally, like it can take a few years if it's aerobically digested. And that few year cycle has been going on for 300 million years without affecting the climate at all. So it's a very rapid turnaround of carbon that originates from the atmosphere and is ends up in animals and plants and then goes back into the atmosphere. So it's a cycle. It's a net zero cycle. Now, when you look at these facts, and I do apologise about my rationality, I'm a scientist, but leather has quite a good story to tell from this point of view. It's biological. Its source of carbon is bio. But this is, I do believe this is a story that we do need to tell. And we need to tell it slightly more effectively than we do right now, because there's a lot of people who would like us to believe the opposite. Now, we can of course work on biodegradability, can't we? That's aerobic decomposition, and that's my mate Dave there. He's bought his compost bin, and if the label says it's compostable, do we just put it in there? Well, that's not true, is it? Because most of what we're talking about when we talk about compostable and biodegradability, we tend to talk about industrial processes which involve collection and infrastructure to do that. But compostability is an excellent way of disposing of old leather products. And this is, I think, where leather scores very highly on the sustainability list. And it's not just about disposal of waste. And I think this is really only something that where the penny dropped with me quite recently, is that if you look up the definition of compost, it's actually decayed organic material that's used to improve soil for growing crops. Okay, and decayed organic material is not plastic, that's leather, isn't it, if we're going to dispose of it that way. So when we talk about compostability, we are talking about replenishing the nutrients in the ground to make sure the plants and crops we grow are nutritious, okay, which is another problem we're facing, isn't it? Now, leather isn't perfect by all means, really. Leather, because of course, have a plastic content with coatings of various thicknesses, backings, etc. It, of course, can have lots of chemicals present in it. But with a little bit of work, that can be made a lot better. As opposed to plastic will always be fossil based. And I apologise for that little joke cartoon there, but I find it personally rather difficult to celebrate biodegradable plastics, which are just going to put fossil carbon in the air in the forms of CO2 or methane, whilst those people celebrating that are quite happy to criticise cattle. And that I think that's a story that we all have to work on. What are we doing about this? Well, Satra's going to next year start or continue a big product. Yes, projects. Leather is a natural choice for footwear, but we need improved testing methods. A lot of the methods that are used right now are kind of based around plastic and producing CO2 and things like that. We need better test methods that bring in the idea of compostability, the fact that the material probably behaves better as a compost if it's not fully degraded and still has large amounts of organic content in it, because the organic content helps the fields and things hold moisture, stops the soil blowing away, things like that. But we do need to work on this, and we need to have better test methods. And for anyone out there who's not familiar with Satra, Satra develops test methods for footwear. That's what we do. And they're standard, basically accepted as standards all around the world. We need to communicate the meaning of the results to end users and consumers, because those are the people that are making the decisions on what they buy. And we need to be very careful how we define things. We need to be a little bit discriminatory between whether it's from a fossil source or whether it's actually from an atmospheric source. And go back to this, the fossil source takes a long time, whereas the biosource is actually quite a repeating cycle. You just only got to look at autumn. It's autumn right now in the UK. The leaves are falling off the trees, they're degrading, and next year they'll be back as leaves. They're generating CO2. Next year there'll be leaves again. But above all, I think we need to be truthful and honest about the test methods. We need proper test methods, and we need to be honest about the work still to be done. Thank you very much for listening. I hope that's been of interest. Thank you.
Thank you very much, Tom, for this excellent presentation, showing again proof that leather is the most sustainable material for footwear. And I'm sure that this is a very valuable contribution to demonstrate this fact compared to other materials. Thank you.
Thank you. And next presentation will be application of kinetics models in leather processing. Yes, it is very important understanding the process to be able to optimize the process and to reduce also cost for the process. This presentation will be is prepared by Ms. Queiroz from Brazil. It is a doctoral student in chemical engineering at the postgraduate program in chemical engineering. She holds master in chemical engineering from the same program. She holds also bachelor degree in chemical engineering from the Federal Institute of Education, Science and Technology. And she works on preparation and characterization of activated carbon, parameter estimation and modeling of absorption and leather processing. Ms. Queiroz, floor is yours. Thank you.
Good afternoon, everyone. I'm Vânia Queiroz. I'm a PhD student from University of Rio Grande do Sul, Brazil, and I will present the work Application of Kinetics Model in Leather Processing. Kinetics are present in almost industrial process. Understand how the kinetic occurs enables the process improvement. For leather processing, few works use kinetic models, even though a wide variety of studies performing kinetic experiments are found. The aim of this work was to evaluate which kinetic models are used in the leather process, as well as to identify whether the hypothesis made in this work. What?
Could you please put your presentation in large screen?
Oh, okay.
Thank you very much.
Yes.
Probably the best option if you use the mirror, if you have two screens to mirror them.
Let me see. Right. The aim of this work was to evaluate which kinetic models are used in the latter process, as well as to identify whether the hypotheses made in these models correspond to what occurs experimentally. The most used models are pseudo-order, pseudo-second order, Weber-Morris, and Segata point and Segata point modified model. These models were applied in the states of unhairing, tanning, and dyeing. The optimization of the process of leather manufacturing allows the use of the proper amount of chemicals needed, reducing the chemicals and the pollution load of wastewater. This can be achieved using kinetic models that permit simulations and predictions, evaluation of the systems under the steady work condition. With mathematical models, it is possible to scale up without repeat experiment. In letter processing, Kinetics studied provide information about the necessary operation time to complete the reaction in bean house, tanning, and wet finish operations. Over the years, a wide variety of kinetic models have been formulated. In applying such models, it is extremely important to follow the assumptions of the models to obtain consistent result. In literature, kinetic models are often used in data processing of wastewater and of letter process. However, few papers use kinetic models for letter processing. The aim of this work was to evaluate which kinetic models have been used to study the steps of processing, as well to identify whether the hypotheses made in these models correspond to what occur experimentally. The Scopus and ScienceDirect database were used to search using the following terms: kinetics and letter, tanning, dyeing, and unhairing. The results were analyzed to eliminate duplicates and inappropriate articles, and then they were categorized as to the stages of letter processing in which the kinetic was evaluated. So many steps in letter manufacturing involve a study adding chemicals that are used done in wet medium performance in drums. These steps require mass transfer from the bed to the house. So it is very important to know of the process. In this presentation, the focus will be on the steps in which kinetic studies were carried out and the works present in the literature. In the unhairing step, the hair can be destroyed, hair burning, or saved, hair saving. To preserve the hair, enzymes were used. To get into the hair roots, the enzymes must diffuse into the hide. Tanning and dyeing steps involve the diffusion and fixation of tanning agents and dyes. In the tanning steps, the fixation must be after the diffusion to avoid that the center of the hide is not tanned. In the dye steps, the two steps may or may not occur in sequence. Depends on the time of depends on the purpose of the letter article. Only superficial dyeing can be done, and the process could be simultaneous. Table 1 presents the main hypothesis made in the deduction of the models, and which step is the limit one of the considering models. In this compilation of kinetic models are indicate its use in different steps of letter processing as found in literature. The Segara point model assumes that the concentration in the bed is constant. It is an empirical model and was used to describe the kinetics of the studies in the works of Kent, Kant 2019 and 2010. The modified Segara point is an empirical model that takes into account the varying exhaustion and also was used by Kant 2009 and 2010. Weber models is a model deduction with Crank's equation and has hypothesis that the bath concentration is constant. The absorption kinetics is instantaneous and the equilibrium isotherm is linear. This model was used by Kant and Satish. The pseudo first order and the pseudo second order are empirical models that assume that the adsorption drive force is the difference between the solid phase concentration at any time and the equilibrium. And at equilibrium, Satish and Kanagaraj used these models to describe the kinetics of the process. The Vickers-Staff models assume that the concentration in the bulk phase is constant and was used by Jian 2011. In literature, the models used are mostly empirical. They are easy to use, but are subjected to operation and process conditions in which they were deduced, and therefore cannot be used to describe the system with conditions different from those determined in its adjustment, which limits its application for provision. The pseudo first order, pseudo second order, Segara point, and Segara point modified models used in the analyzed articles were using their linearized form. The correlation coefficients or sum of squares was used as an index to quality in fitting the data to the model. Transforming a nonlinear equation into a linear equation involves assumptions, and the obtained results can be very undermined. This leads to data distortion and consequently results that violates the standard least square assumptions of variance and normality. Jian used enzymes in the unhairy steps. The good fit of the Vickers-Staff models suggests that enzymes unhairing by protease is a diffusion controlled process at the initial stage, where Vickers-Staff can be used only in a short time. The papers study the diffusion stage, which is very important due to the crossing of the guarantee the stabilization of the height in case of. So only kinetic models that are based on diffusion should be used. However, pseudo first order and pseudo second order are based on reaction and were used. Satish 2019 study chromic tanning used Weber model, pseudo second order and pseudo first order. The best fit model has been chosen based on linear regression coefficients and based on the linear regression coefficients and square sum of errors. The results indicate that the Weber model was the best kinetic model. Kant 2010 based the results of the shape of the isotherm and the linear regression coefficients value to support the modified Segara point model for absorption of tanning. Different kinetic models are reported in literature possibly due to different types of dye used. They have different rates of adsorption due to the difference in their chemical structure. Kant 2009 report the application of enzyme as protease for the improvement of the exhaustion of dyes. He used the models of Segara point, modified Segara point, and Weber models. Kanagaraj 2016 used a couple line trimming waste, starch, and polyvinyl alcohol as a high-performance auxiliary in dyeing. The rate of absorption of dye inside the porous layer was represented by pseudo-second-order kinetics. And Kinetics 2011 used a nanoparticle polymer to enhance the dye uptake. The rate of the mass absorption inside the porous layer was represented by pseudo-second-order kinetics. As conclusion, this study identified a few works focused on the study of layer processing kinetics. These works use empirical models or simplification of phenomenological models. The models have as main limitations the fact of there are only valid under specific conditions in which they were deduced, or in the case of simplified models under conditions consideration for simplifications. The models are usually based on their linearized form. However, it is not very appropriate to use the linear methods to determine kinetic parameters, because transforming a nonlinear kinetic model into a linearized form tends to change the error distribution and therefore distort the parameters. Thus, it is advised that more research in this regard should be carried out in order to better understand the kinetics of the inherent tuning and dyeing steps. Furthermore, the use of phenomenological models should be encouraged. These are the references used in these presentations. And thank you, everybody.
Yes, so thank you for a very interesting presentation. I think it is really important also for us to understand kinetics and also what is happening in drums, as proper understanding will also save cost, time, and energy needed for the process. So many thanks for the presentation.
Thank you very much. I would like to present the next speaker, Dr. Amen Jochen from Germany. He has a PhD degree in the field of natural product synthesis, and he worked as a project leader in medicinal chemistry for Eli Lilly in Hamburg, Germany. He is the group leader in medicinal chemistry for the European Molecular Biology Lab in Heidelberg, Germany, for production support, for polycondensates, and R&D wet end for the leather department at BASF, and currently is working with Stahl with the same role as before with BASF. So please, Dr. Amen Jochen, go ahead.
Okay, estimated guests, distinguished leather technicians, fellow leather chemists, it would be my pleasure to present to you a project in which we looked for alternatives for resin retaining agents. We found it and we applied it on leather.
I'm sorry to interrupt. Please press on the slide view button, which is circulated underneath. You can see the thing, guys. And then we can see the presentation in big. Yes, perfect. Thank you.
Now you should be able to see the second slide.
Yes.
Titled Wet End Chemistry. Okay, this is basically the portfolio leather technicians use to retain leathers. Biggest group is synthans. There can be distinguished between phenolic synthans and bisphenol S-based synthans.
Sorry again, you have to share again your presentation. We lost the presentation.
Okay. Rest monomers in this chemistry can be phenol and formaldehyde. Formaldehyde, there has been a lot of literature out how to resolve this, and there are also a lot of good products on the market that have resolved this issue. Bisphenol S, as we learned this morning, is a hot topic, especially in Europe. And I think Martin Kleban pointed out what we need to know about this rest monomer that's really high on the list in Europe. Second group is the one that we will focus on today. These are the so-called resin retaining agents. They're either melamine urea formaldehyde condensates or urea formaldehyde condensates. Resin is a little critical word in retanning. In wet end, we consider this chemistry among this wording. The finishing colleagues in many cases consider polyacrylates as resin. So here we have to distinguish between wet and finishing. Rest monomer is certainly the formaldehyde, as we'll see 2 slides from now. Last group is the polymeric, polyacrylic-based retaining agents. We'll not go into them today, but we will note that they show a very good light fastness. And as you can see on the lower right-hand side of the slide, with the resins, light fastness, the yellowing is not so bad, but it is significant and measurable. And with the synthans, it depends on the chemistry how good you get. Here you see an example of a urea formaldehyde condensate. This chemistry became very important in the 1930s when it was applied as an impregnating resin for chipboards. This made wood industry far more sustainable because they had a lot of cutting waste, and this cutting waste, with the help of this chemistry, could be converted into value. This chemistry was further developed later on by the incorporation of melamine that you see in the center of the structure. This made the resins more applicable, and the chipboards became fire resistant or more fire resistant. And then this chemistry was further developed. It became water soluble by the introduction of these sulfonic acid groups, and then it could be used as a retanning agent. This trick was not new because it's the same as what has been done in synthans. Synthans are basically water soluble bakelite plastic material that was invented. So the melamine urea formaldehydes are quite old products by now. Maybe they are at the end of their life cycle. Many products are spray dried. This affords a lot of energy. Their performance strength is certainly filling of the flanks and good light fastness. And the issue is they release formaldehyde. This is easy to understand if we look at how they are made. We let a melamine and a urea attack a formaldehyde from both sides. Then we get a new bridge between these two moieties. The water is released, and this reaction usually takes place at basic pH. We're almost done. Now we need to make this water soluble. And here we apply a second formaldehyde condensation in the presence of the sulfide. This is what you have also in red wine or white wine to stabilize. That's very common chemical. Then you can make this chemistry water soluble. The bad news is that this reaction of formation is reversible. And the reversible effect of the synthesis, the hydrolysis. So under acidic pH, you can go the other way to a minor extent. Then water will attack this bond and will release formaldehyde and this happens in the presence of water and acid. Now, if we think that leathers brought into the market in many cases have pHs of 5 to 6, but barely ever 8 or 9, the best thing to make this, to conserve this, would be to go to basic pHs, which we cannot do for technical reasons. Another way one could do is to think of giving scavengers in here that would scavenge the formaldehyde, but they would reduce the problem here, but they would not reduce the problem of the hydrolysis and of making the chains smaller. So this was one of the initiations of our project. We compared also scavenger containing products with pure melamine resins. And we saw that, yes, if you put a scavenger in there, the formaldehyde release on crust seems to be smaller, but only initially. Later on, if you measure the same level again, 3-6 months later, we see formaldehyde values rising. So we thought this is not a way to go to resolve the problem. We wanted to focus on a new chemistry called melamine ethoxylates. And how are these made, or what is known about them? We wanted to go, so we wanted to replace the formaldehyde. We wanted to stick to the melamine, basically for performance reasons. We wanted to go for liquid products to save energy and to bring a green aspect into this project. We wanted to see if we can get a patent on this. And we wanted to use also partially starting materials if possible. Now we are in the materials and methods section. We had 2 ways of forming, of reacting melamine with to get a melamine ethoxylate. The first reaction is with an alkane oxide, so ethylene oxide. Second would be to go for the comparable carbonate that you see here. We clearly focused the upper process because here we would release one equivalent of carbon dioxide, and sustainability is all about, or a lot about, reducing CO2 emissions. So our chemistry was ready. Then we bumped into our first problem. Ethylene oxide is a gas. Melamine is not so reactive. It is a solid, high melting point. So we needed to get the reaction started. We needed an initiation, and we needed to solubilize this. We worked with quite a few solvents, and our favorite one was glycerine because it's renewable and it worked quite well. And now we are in the results and discussion phase. Here we screen for the chemistry. How much ethylene oxide do we have to put on top of the melamine diluted or dissolved in glycerine? And we could really follow this path by increasing amounts. We could see different effects in retaining in application. With small amounts, we start to see a retaining effect. With still quite small amounts, we saw a good retaining effect, quite comparable to the resins that we were up against. If we increase the chain length, we could not see a huge improvement. And if we really exceed the chain length, then we move away from the effect that we saw here, from the resin retaining effect, and we had a retaining effect that could also be obtained with pure ethylene, polyethylene glycol, which is this reaction of ethylene oxide reacted with itself with no. Now we made 6 different leather articles. In retaining, we can determine the leather properties of the articles. We use 6 different recipes that use resins, and we replace them 1-to-1 active material with our pilot batch that we had upscaled out of our chemistry by then. And you can see the color strength was also always a good stronghold of this chemistry. With filling, we clearly observed a little less filling than we wanted to have with that we used to get with the resins. The softness we could see in 3 articles, a positive effect, and also important, the grain tightness, we were always in the level that we were up against. In this slide, you can see an example of the color strength. So this is crust at the end, including fat liquor and dye, and we have the exact amount, same amount of dye in both retaining procedures, left with a standard resin, right hand with our pilot batch. And so we have a color strength benefit here. And if you look at the light fastness below, you see that the light fastness of the resin retaining agent was clearly improved. We're now almost in the range of polymeric retaining agents. So this is basically best in class. And now I come to the summary. The melamine ethoxylates show a stronghold. Color strength, they have good grain tightness, similar softness, but less filling. We think that this needs to be addressed in the retaining recipe. We can offer an alternative to resins. And the melamine ethoxylates have no formaldehyde. We have the innovation that we have a liquid product that doesn't need to be spray dried. So in other products which are made in the presence of water, the water is in many cases sprayed away. This costs a lot of energy. We are not in this, we don't have to overcome this problem. And then if you, on the other hand, say, I made my chemistry in water, I ship the product as such to the customer, customers might argue that now water is shipped, this we can also say. We could apply partially renewable starting material, which was the glycerine. The glycerine could react with ethylene oxide itself too. And we saw indications that this happens to a small extent, but we don't see a problem. What's important is that we see that the melamine is ethoxylated, because melamine as a starting material is also not uncritical. In Europe, it is listed with the H value of 361. That means 361F, that reduce fertility. And there are also some studies run or thumbed up by the IARC, the International Agency for Research on Cancer. They have investigated melamine as such. The toxicity is not so large, but they could see in rodents that some tumors involved there. So we have to be sure that we react in melamine entirely, and this we could see. Finally, yeah, we saw better fastness properties. There we have a clear advantage for the current chemistry, and we could get a patent on that, which is also quite practical for this presentation, because otherwise I could not reveal all these details. So this was the team doing it. It was a joint effort between Stahl and BASF, which worked together for historical reasons, and Andreas Kunst. He ran the chemistry in his lab, also in the pilot plant. So I owe him gratitude for that. I'm part of Ralf Blach's R&D organization, Untitled Chapter support. So my role is not to bring so much into R&D. My role is to bring things out of R&D, first into vessels and then into productions. And now I want to thank you for surviving 15 minutes of highly concentrated chemistry. Congratulations.
Thank you very much, Jochen, for this excellent presentation showing applied research to solve the issues of free formaldehyde and the formation which we measure in the emissions. So a formaldehyde-free melamine ethoxylate will be very beneficial to solve the emission issues. Also a further advantage you showed, it's partly renewable again and a liquid product versus the commonly applied resins, which are more difficult to apply in process. So it's a very innovative product, and it would be very interesting. It was very interesting to learn about it. Thank you very much. Good. We have heard 4 excellent presentations, and I would like to come now to the question and answers. I'm sure you have lots of questions addressing the presentations we have heard. And we'll come to the first question to Daniel Pernigiotti from Dietrich Deckmeier. So from where do you get the PCF data of all the individual chemicals?
The PCR or PC?
PCF.
Okay, sorry, because we use the different acronyms, CFP, carbon footprint of products. So sorry for that. Yes, we have normally we use a database, and then we open a very important discussion on the data quality, because obviously some chemical products are already present in the database. In other cases, we need to work in the direction of see similarity on comparable chemical products. So there is a study behind each chemical products to identify the emission factor.
Thank you very much for your answer. We have here another question. Again for you, Daniel Pernigiotti. So thank you. The question comes from the audience. Thank you for the informative presentation. Please give us an opinion how important it is to include lifetime of usage of products into LCAs, in regard that lifetime will have an impact of overall GHG impact of an product.
Thank you so much for this question. It's very, very important. In my view, it's crucial in the leather sector, because we know the leather products are better performance in comparison with other synthetic material, and to give more value of the product is fundamental to stress the aspects of the duration of the life cycle. In this particular case, we had some experience with the footwear products, and unfortunately, there are not yet some methodology to quantify the duration in terms of time of footwear products. So this is an area where we need to work together still more. And I'm sorry that Tom, I don't believe Tom is here today, but I think his organization is one of the most crucial in the direction to develop a new methodology for the quantification of the technical characteristics of the food weather products. And yes, I like to stress the importance of these aspects, and I will be more than happy to work with other partners in this direction.
Thank you very much. So we have here a question for Tom from Karl Flowers. Tom, you're an scientist, but does the industry need more leather politicians that help fight the anti-leather ideology? More importantly, can scientists get the data that the leather politicians need to fight the ideology? It's a very good question. Tom, if you're here, please, if you could answer Karl Flowers.
Hi, sorry, I wasn't being allowed to unmute. Yeah, I know Carl, and it's a great chap. I love it. Hello, everybody, by the way. Sorry I couldn't be there in person. It's a very, very good question. Yeah, leather politicians, that's a lot. I really like that. You know, yes, we do. I think, and we need data. And I don't want to be controversial, but we need proper data, because going back to my presentation, you know, that there are people that don't like leather, and for various reasons, and they don't always tell the truth, and they don't always present a scientific argument. You know, the argument in my presentation, my argument is, you know, don't have a go at cattle if you claim the solution is to put fossil carbon in the atmosphere. But we do need leather. We definitely need leather politicians, and it strays. You know, and again, I don't want to be controversial, but you know, obviously we've got car companies that are leaving leather and going for synthetics and things like that. But I mean, you know, and even new materials, you know, like the apples and the pineapple leaves and that kind of thing. You know, you wouldn't be very happy if I sold you leather that was only 10% leather and 90% plastic. You know, I don't think you can sell a product and label it apple if it's 80 or 90% actually polyurethane. So we do this, and this is the point of my presentation, is that we need to be, well, first of all, we don't need to tell stories, we need to be honest. And we need to provide, we need ambassadors, I think, that are rational and tell the truth, because I use the analogy of a war, but you know, we keep rather quiet when people are telling stories about us, and I think we should be presenting proper scientific data to these things. I think it's, I don't want to use the term greenwash, but it does apply to basically all sustainability arguments where, you know, yeah, electric cars are fine as long as we completely ignore the source of the power. You know, and there's questions about whether it comes from solar, which is, or wind, but most of it comes from coal still. So again, it's I think we need to tell the truth and be honest, stand up and be honest. And yeah, well done, Carl.
Thank you very much, Tom. It's so true.
Ambassadors. Yeah.
So we have another incoming question from Billy Mendes. Again for Tom, thank you for your presentation. My question to Tom is, this time advanced technologies are used to produce materials that resemble pure leather. Can you please suggest a proven testing method to distinguish synthetics from pure leathers?
I don't have a great depth of knowledge on this, but as far as I'm aware, a lot of the test methods are kind of borrowed from plastic methods, and I think, you know, again, we have to know, if we're going to talk about sustainability, we can't avoid talking about carbon, and we need to consider where the source of the carbon comes from. If the question here is about for the use in footwear, and I think I'm not sure what the subject of the question is, but if it's for footwear, and we get this asked a lot, is materials suitable for footwear? Well, it's a bunch of test methods that are used for footwear materials, and it's the function that's important, not the material. So, you know, any material can be used for footwear, but as long as it passes footwear tests, like flexing tests, abrasion resistance, blah blah blah. If that's a subject of the question, so the test methods for the materials suitability are the same. As far as I don't know how to use the word fakery, but faux. If we're talking about faux materials, FAUX, we talk about materials, and we talk about faux fur a lot. We talk about materials that are actually, you know, they're not cheap, they're not fake, they're actually very, very cleverly engineered to give the same properties as leather. And we use microscopy for that, because sometimes it's very, very difficult to actually determine whether a material is leather or not. Some of these materials are very, very good. And that's the same for fur products as well. You know, but fur is an incredibly well insulating material. It's actually quite difficult to make faux fur. It takes a lot of technology, a lot of science. So we use microscopy to distinguish one from the other, to identify them. And we do actually offer a service where you can send us materials and say, basically the question is this leather? Sometimes it takes quite a long time to actually determine that, because some of them are quite clever. If I haven't answered the question, you can email me, and I'll do it offline.
Yes, thank you very much, Tom. Very good answer. So we have another question from Harrison Mungai from the audience. Mr. Baez, very good presentation.
Thank you.
How to differentiate leathers from artificial materials visually without using any equipment? Can leather be made from other sources beside animals? And how long can leather last?
Good question. Well, number one, yes, we do tend to use visual techniques when we get asked questions, is this leather? And there is a British standard that defines what leather is. So certainly in the UK, as far as trading standards are concerned, there is actually a definition of leather. So if I was very mean, if I was going to be mean to anybody, yeah, you can't. If it's not an animal source, it's definitely not leather. It can't be described as leather. But to be positive, yes, there are, and a lot of my work also involves quite, as I mentioned, quite technical synthetics. You know, microfibers are pretty good, especially if in warm, humid environments. You know, leather absorbs a lot of moisture. And when you get a high moisture content in materials, or a variable moisture content, that will impact things like breathability and moisture management, what we call moisture management, which is the process of removing perspiration away from the hose so that the hose stays dry. And if the hose stays dry, you tend to feel more comfortable. And there are some very good alternatives. They don't quite come up to leather in terms of abrasion resistance, and again, when we talk about sustainability, we talk about durability and a long life and repairability, and leather is extremely good at this. You can restitch. I mean, I've got welted shoes that have been resold 3 or 4 times, and they're still perfectly okay. Most synthetics won't stand up to that kind of restitching. Although someone is going to tell me about one that does in 5 minutes, I'm sure. But yeah, but when we differentiate leather from artificial materials, or let's just say non-leathers, reconstituted recycled leather, for example, we do use visual techniques. We use microscopy. We've got some very good microscopes. Anybody who's decided to remember, actually, I've just done a webinar on how we use microscopes, and I did focus a lot on how we use microscopes to identify materials by looking very closely at them, looking at the fibre structure of those materials. Yes, there are, question 2, there are very good alternatives that are coming online. I mean, the technology is growing, people are looking at them very carefully, but I come back to my original comment is I don't think it's entirely fair to identify material as being Apple, for example, made from Apple, when it's only 20% Apple. We wouldn't say that about leather. You know, if the leather had a 80% coating of PU on it, we wouldn't call it leather. So I think whilst it's coming online, we do see, you know, Apple with a big capital A, not polyurethane with a big P, with a tiny little apple afterwards that says it's got a bit of apple in it, and that's not entirely honest, is it? And I think that's what we're up against. How long can leather last? Well, it lasts a very long time. I mean, it's strange that in the right conditions, you know, if you look at very ancient civilizations, we know most of what we know about them is what they drew on cave walls and their shoes, shoes that survived. And some of these shoes are made, I think the oldest shoe that was ever found is actually made out of flax, out of reeds. I think it was Egyptian. So yes, they can last in the right conditions. They can last a long time. But you know, they also the material offers itself to biodegradability. And you know, we're not. I don't think anybody's probably a fan of Hitchhiker's Guide to the Galaxy, where civilizations end with a compressed layer of footwear. We're not at that stage yet, but it can last a very long time, especially if it's cared for. And I think this is a good thing about leather, is if you care about it and you look after it, you use the correct care products. There are many good ones available. I have shoes that are 30 years old. I'm probably unusual, and they are as good as new. On the other hand, it offers itself to biodegradability, and I'm coming from a point of view of working for a company that spent 102 years trying to stop shoes falling apart. So yeah, it can last if you can look. You have 2 options with the leather. You can look after it, and you can treat it well, and feed it with various you know, waxes and things like that. It will last a very long time. It'll look good for a long time. But you have this other option with leather where it actually is quite biodegradable and can be easily decomposed into things like compost and maintain an organic content, which is important. With fertilizer, doesn't do that. Compost does. Compost puts organic material back in the ground, and I'll borrow something that Carl said the other day, is that the important thing about putting nutrition in fields is to make the plants nutritious. They'll grow anyway, but their nutrition level that's in those plants will depend on the nutrition that's available in the soil. I'm sorry if I go on too long. Just stop me.
Thank you very much, Tom. So we have here a question for Vania Guerreros. Excellent presentation. Did the models verified practically or experimentally in the real unhairing, tanning, and dyeing activities? Question comes from Mulatu Pirano.
Well, Oh, thank you for the question, Mulato. Yes, the works that use these models do experiments, but my presentation was a review of these models. And what it was just not say is that they are often used, but not say too much about the conditions for the applications. I don't know if I answered the question.
Yes, thank you very much.
Okay.
So let's see, there are many questions coming in. And we have a question from Mr. Prasad Mupa for Jochem Amen. Congratulations for the interesting work on new fillers. If I understood correctly, glycerol was used as a solvent for the amine and ethylene oxide reaction. Final product is a spray dried without glycerol or with glycerol on leather. That's the question.
Yeah, we didn't spray dry the product on purpose because also the glycerine is in there, and glycerine would not behave very well in a spray drying. And but yeah, glycerine is also in the final product. That's true.
Excellent. Thank you very much, Jochen. And we have a question again for Mrs. Kerios. Thank you so much for your presentation. Could you please cross-check whether your study was about application of kinetic orders or RxNS instead of kinetic models? Because kinetic models are fractional occupancy and combinance. Question comes from Michael Kirei.
Okay, thank you, Michael, for the question. The study was a review with which models are used in the letter processing steps, and the ones found use the kinetics of these steps using these models. I do not see the application for fractional occupants of combinants and in these works, but I will check and see if I found something more like something more about the fractional occupancy of combinants.
Thank you very much, Ms. Kerios. We still have another question coming. Good. I think yeah, that was our question and answer sessions. Very good presentations and also excellent questions and answers. And I think that made all for us much clearer about new sustainable developments. And I would like to thank the audience and hand over for some words to Mr. Kral from UNIDO. Thank you very much.
Yes, thank you. I think that all four presentations were very good, and we have something about transparency, also how to present and to have some politicians which will defend the leather. And of course, that kinetics models would be also very important, or models for our industry. And the last presentation about new resins was also very fundamental and very interesting. So I think that now Professor McCann, he can also present certificates to the presenters. Thank you very much.
Thank you. Thank you very much, our great moderators, as well as excellent presenters. I'm sure our IT unit is now ready to display the certificates of the participants. Yes, I think our certificates now are displayed. as you see. Yes. Thank you. Okay. We have seen those samples of certificates. Thank you very much to the IT unit for that good work. Thank you all participants. I think with this, we will end the morning session. We will break for lunch and we'll come back after lunch. Let us now, we are at around 13. Let us come at 14:30. As usual, we are, no, the other exercise will be at a later stage, coffee break. But for our session, yeah, let us come back at 14:30. That will be good. Thank you very much.